Okay, so we got this guy. So at some point, we're gonna turn you loose with this thing, and the idea is that it is kind of written for high school students, but what we want you to do is to there's these step-by-step instructions, and you basically in your logbook you write up, okay, here's our apparatus, and here's what we did first, here's what we did second, and you just go through these steps. And in fact, this is nice here because in the beginning, like, let's see, I'm on page 5 and page 5, I think, no, page 6, 7. So these are like, you know how I've said, if you look at the format for the logbook, you have the first part of your data section is describing how the apparatus works. And so there you go. This is here, and you can walk. It walks you through it, and you can. It has a facility for taking screenshots, and it's pretty nifty. And what they've done is they've set this thing up so you're measuring the magnetic field in Bermuda. But I went ahead to this website that's embedded into this PDF, and oh yeah, here we go. And I have the information from my home address. This is amazing. So I can actually, I have the real instruments here, so uh, I'm going to do a few demos here in the beginning, and then we're going to turn you loose. And then in the meantime, I'm going to try taking some data with the real apparatus. No, that's right. I have to get my camera act together here um, so I can do the intro. So why don't you guys, while I'm getting myself going on here, why don't you guys get started? Let me take a look. No, oh yeah, here we go. Explore the apparatus. So that starts on page 3. So why don't you all get going on that? And then Philip is here, and I have to figure out if there's a way for you, Philip, to always be a co-host. That way, if um, yeah, do you want to make of this meeting? Yes. So because in the event that I wasn't able to be back here, I have the meeting set up so you guys have, you know, that you can join without me being around. But and you could interact with Philip anyway. But if he can't be a host, then there's some features that are disabled for him. And anyway, so as I said here, please start in with this on page 3, taking notes. And when I get the demos ready here, we'll take a break, and because remember, part of the objectives is the right-hand rule for currents and wires, and how then you can take a wire and make currents and wires in the magnetic field that they produce, and then you take the wire and twist it into a coil, and then how it works from there. All right, so I'm going to mute myself. Both Philip and I are here, and you have the chat window to talk to each other. I think we'll hold off on breakout rooms for the time being, in case there's questions that everybody can hear what the question might be and or the answer. Are there any are there any questions at the moment? Oh, and just to be sure, where is? Yeah, here we go. I just only, oh yeah, I showed you this, right? I only just posted it, but it is there. Very good. And then I've got this magnetic sensor as well, and we'll see if we can do, um, I'm interested at the end of the regular lab manual is a way to measure the magnetic field by timing the oscillations of a bar magnet. And I have this idea that and I have this magnetic sensor, and I have the coils there behind me that we can see if we can set a field like our own field, that we know exactly what it is, and then we can time the oscillations, and we'll see, we can make a double check on how good that method actually is. Okay. Anyway, so again, please get going there, and I'll join you as soon as I get myself ready here. And again, oh yeah, I haven't. Oh, question. Where? Oh, you got it, James. Okay, good. Very good. And I can hear you. I'm just going to mute, but I have these new wireless headphones, so I'm going to leave them on. And of course, Philip is here as well. So I'll be able to hear you, even though I'm not going to be right here in front of my terminal for a little while. I'm ready to go here. We'll find out. Best way to find out is to try. So maybe I'll give people a minute or two in case they're in the middle of something, they're writing something down. Okay. So one assumes, I don't know, week 8, would you be in doing magnetic fields yet in lecture? I don't know. It's funny. Well, did I teach? I haven't taught 2200, I think, since the spring. Excuse me. Excuse me. I'm burping a little bit and sucked down my Gatorade too quickly. One assumes we all know what a magnet is, a bar magnet, and maybe even a horseshoe magnet. You know, you may even have something on your refrigerator. So we all kind of know, we know about plus, like in electrostatics, opposites attract, likes repel, just like, so magnets have a similar aspect to them. As far as we know, there's only 2 poles, a north pole and a south pole. But one thing is, though, that's very different, which is kind of weird in a way, because it turns out that electricity and magnetism are essentially manifestations of the same thing. So, in fact, in the field of elementary particle physics, of which I am an elementary particle physicist, the holy grail is to combine the 4 forces of nature. And so we at least know from physics 2100 about gravity, and we've talked a little bit about that gravity. And then, of course, now in physics 2200, we have E&M, and it's electromagnetism. And remember, the principal thing here is that any forces associated with electromagnetism are about 10 to the 35 times any force of gravity, which is just amazing. I mean, this is one of the mysteries of our world, that why is there such a huge difference? In fact, it's quite necessary. Well, it's not. It's necessary in the sense that if it wasn't true, our world would look very different. That doesn't necessarily mean that different is bad. We may not exist in a form that we exist in, as we are, but it doesn't mean it's bad. But it's weird. And, you know, elementary particle physicists search for meaning and underlying meaning. And at the moment, the thing that's really coming on in the last 5 to 10 years is the so-called multiverse, meaning that there's infinite number of parallel universes, and we just happen to live in one. Like every time, like at the Big Bang, So there was like when the Big Bang happened, it spawned an infinite number of universes, and in every universe where the Big Bang happened, you had this superheated material that cooled down and coalesced into particles. Well, in principle, it did in our universe. And then all the physical laws, like how strong gravity is, remember the capital G constant, and how strong E and M is, there's either the epsilon sub zero or the K constant, uh, could all be different in each universe. And we just happen to live in one that has the certain set of constants that produces us and also makes the world predictable. There could be universes where the world is completely random, and that would mean that there's no survival benefit to having intelligence, right? We live in a world that's predictable, so there's a survival benefit to have a brain and to be self-aware. And so then eventually we're here because there's that push and natural selection. So then on top, the other two forces are, and I never see, I don't know why, I guess just because it sounds good, the weak nuclear force, but it's never been described as like distance and force. And then the strong nuclear force. So the weak nuclear force has to do with some radioactive decays. It's pretty intriguing because the, for example, you probably know something about a photon. And a photon is the information carrier for the electromagnetic force. So, of course, we think of it in terms of light, but it turns out you remember the very first thing you learned was F equals K Q1 Q2 over R squared. So if you have two charges and they feel a force between them, and so there's the field formulation, which we're using, but the particle formulation says that these two guys are shooting photons at each other. And the photons are like little telegrams, and it's saying, hey, yo, Mr. Positive Charge, I'm Miss Negative Charge, and since we're this far apart, we're supposed to have this much force between us. So the fancy term for this is a vector boson. And a boson just means that it's something like a photon, whereas an electron and a proton are called fermions. And that's just like spin up, spin down. If you remember from chemistry, you have like the 1s level, but you get two electrons in the 1s level. One is spin up, one is spin down. Whereas bosons don't have any spin. And there's lots of implications. And vector just means transmitting agent. So a mosquito is a vector for malaria. And as you may know, a photon is massless and it does not feel the Coulomb force. So you have to have a charge for the Coulomb force. A photon doesn't feel the Coulomb force. Photons, in fact, feel gravity. I don't know if you knew that. That's one of the ways we can see black holes, because the black hole's gravity is so intense it bends the photons. In fact, in 1919, people watched for the Mercury appearing from behind the sun, and it turns out that because the Mercury is so close to the sun, and that the light has to go past the sun when it just first comes out from behind the sun, it bends the photons ever so slightly. And then when we can see Mercury a fraction of a second before it actually comes out from behind the sun by line of sight. and this is how that Einstein didn't prove that relativity was true, general relativity, but it pretty much said that general relativity was correct because Einstein predicted that, and everybody thought he was nuts, and it turns out he was right. Um, so next is then the weak nuclear force. The weird thing, the simplest way to, well, there's beta decay, but what happens is in a nucleus, protons and neutrons actually change back and forth into each other, and they know how to do that because they talk to each other with these particles called a W plus or a W minus, and there's also a Z zero or a Z zero. And the weird thing is, though, that these are the vector bosons. So they exchange these particles to know they have a mass. A mass of a W or a Z is equal to 90 times the mass of the proton. And it's like, WTF? How can that be possible? But what happens is that's why we don't see these weak interactions except inside the nucleus because and yeah, because radiation is a nuclear reaction. Because what happens is, well, if the W particle doesn't exist, if it can limit its time of existence, and it's allowed to exist briefly, and it appears out of the vacuum. It's called. It's pretty trippy. I'll maybe talk about that another time. But because the proton and the neutron are so close together, the time it takes for a W particle to go from the proton to the neutron is so short. We have this thing called an uncertainty principle, delta E times delta T, and it has to be greater than this thing called Planck's constant, which you may have seen before. And Planck's constant is about 10 to the negative 34. So it has to exist for a very, very brief time. And if it's less than that, then it can have any energy it wants, as long as it only exists for a brief time. But we also know that uh, Einstein's equation is actually written like this: E over c squared. So it can have, if it exists briefly enough, it can have any energy it wants. So we can produce a 90 GeV particle, 90 times the mass of a proton, as long as it doesn't live very long. It's just amazing. Mother Nature is so freaking cool. And then the strong nuclear force has a vector boson called a gluon. And now the strong nuclear force is able to pull two protons together and overcome E and M force, which is already titanic. And so, but it only operates on the order of femtometers, 10 to the minus 15 meters. And if they get further apart than that, then they repel each other. And this is why things like uranium, a uranium nucleus is so huge that the protons on the outskirts are like, hey man, I can get away because the electromagnetic force is beginning to get strong enough to push me out. It's overcoming the strong nuclear force. Now, the really cool and weird thing about the strong nuclear force is that gluons feel the strong force. So what that means is that when I put two, they're called quarks. If I put quark one, and let's see, if the red quark and a blue quark close together, their force is almost about zero. It's it becomes, as they get very close together, the force becomes zero. And if I start to pull them apart, all these gluons start coming here, and the force actually increases as R increases. It's very weird. And it took us a long time to see why. And by looking at the interactions of these protons and collisions, we finally figured out what was going on. Anyways, the holy grail is to put all of these forces together in one theory. Einstein tried doing it throughout his life, and a variety of people have worked on it and still do. Right now, we can put together E and M, the weak and the strong forces, but gravity is so different, so much weaker. We just don't know how to do anything with it. So, anyways, having said all that, sorry I went off on a tangent there, but you are supposed to learn something about elementary particles in class in 2200, and I don't no, nobody in our department has. Well, no, Professor Aniol, but I don't think he teaches 2200 anymore. So, anyways, getting back on task, one of the weird things about magnets is that they don't, when you break it in half, instead of getting an isolated north and a south pole, you end up with two complete magnets that each have a north and a south pole. And that's a big deal because what that means is well, there's a couple reasons for what it means too, not just simply because of the monopoles, but the force. There's a homework problem that you might get. The force of magnetism is about equal to the force of electricity divided by c squared. And so remember, we talked about the titanic forces of the E and M force, that if something starts to bend and a possible charge imbalance could happen, Mother Nature works so hard to make sure that doesn't happen. And in metals, because of the mobile electrons, they're allowed to bend. And I think I broke a piece of wood. I've broken all my handy pieces of wood. Well, plastic will bend, but not quite as much before it breaks, or maybe it'll deform. Different things depending on the material. So the point too is that one thing to notice then is that if Mother Nature wasn't so big on addressing these imbalances, we would never even know that the magnetic fields exist. And I see in this future slide, I'll talk more about why this is true. It has something to do with not having isolated poles, but I'll get back to that in a moment. One thing that we have to, I noticed over the semesters that I've been teaching 2200, that it's important to understand. And so I guess then this is something I wrestle with the pedagogy here. So one of the rules that makes magnetic fields weak, and I have to state it now because it's important to understand this picture of the Earth, that a magnetic field line has to, and this is really, really important, the magnetic field line has to start at a north and it has to end at a south. So the field lines start at north and they must end at a south. Might as well skip ahead then. Let's switch these slides. It must start at a north and it must end at a south. They're not allowed to go off into infinity the same way that an E field line can. I mean, field lines can go off, but because of this property, they go down in strength faster than 1 over r squared. And the weird thing is that well, at least for a permanent magnet, there's no equation of force. You can't just say that a magnet has a certain amount of magnet charge and I put another magnet nearby. How strong will the attraction be between them? It's pretty weird. But it's folded in, and I tell you what, man, even couple years ago, I was in Korea. My boss and I would, at coffee break, we would talk about this and trying to wrap our heads around it. If in a constant magnetic field, an object, if I put a magnet in a constant magnetic field, you're going to learn it doesn't feel a force, and I can demonstrate that. It can feel a twisting force, but it can't feel like a force of translation. And that has to do with the nature of the cross product and thing called circulation of a field. And I it just tell you what, I can understand it in some deep level, but I can't enunciate it. But I'll talk about it some more just to make sure we understand at least the ramifications. Now, excuse me. So one thing I realized we have to be clear on how a magnet points. I mean, a compass points. So you see how it turns out the Earth, the magnetic north pole of the Earth, turns out is actually a south pole. Although, to be sure, there's nothing special about the words south and north or east and plus and minus. I'm sure if people knew beforehand that electrons were the charge carriers, they would either say that they were plus and the protons were minus. But since all the rules of E&M were worked out before we knew what was really going on inside the wires, we're stuck with it. So, anyways, of course, north and south they must have been defined long ago before. Well, magnets. People know about magnets. The ancient Greeks did. They would find these rocks and then they could take an it's was it well, they would lodestone or magnetite, but you'd find this lumpy rock and they noticed that pieces of iron would stick to it. So they could take a piece of iron, and if you take the rock and you stroke it along the iron, you can create a north and south pole. It's fragile. It doesn't last really long, and it can, if you drop it, for example, it'll lose its magnetic field. But you can put it on a cork, float it in some water, and you have yourself a compass. So, anyways, as we can see there, the compass follows along the magnetic field lines. And so the arrow that points from north to south, the compass itself is parallel to that. And the north end of the compass, the red mark, it is a magnetic north. And it lines up the way you see in this picture. And I'm going to show that in a few minutes as well. But people find that confusing, and we have to get it down straight. And it's also just helpful to think about it, and because when you deal with coils of wire, just think about if the compass could come in like this, then for everything to be consistent, it would have to point like that. So this is a is this actually, no, this is just a picture. This is a demo simulation that it's not live here in this PowerPoint. I don't think so. Let's just double check. Hold on a sec. No, it's just an image file. Okay. Anyways, there's this. In lecture I show this off, but you can see the other compasses needles here. This one can move around in the simulation, so you can demonstrate this. And then just FYI, we think that there's a magnetic field. The Earth has a magnetic field because even though the Earth is 4 billion years old, there's still a liquid core. And apparently, I mean, I haven't checked lately, but the Earth has cooled off much more slowly than most. I mean, there's probably other examples, but if you took a bunch of dust particles, had them coalesce into a planet, and then had them cool down and solidify, you would expect that the materials would be pretty much homogeneously mixed. But what turns out, apparently, our planet is got a lot of radioactive material, enough radioactive material that it's cooled down much more slowly, and that's allowed the heavier elements to sort of sink down into the middle. And so the feeling is there's a metallic core, nickel, I think is again, I haven't checked lately. And the Earth also has a net charge. And so you would imagine that with this nicely conducting core surrounded by less conducting, that there's a net charge on this core too. And because we know that they'll migrate to the surface, uh, and even though, okay, at a sphere, they won't be moving here at the top, but if you think about something rotating, so if we're looking down at there, so if this is R, and we have omega and is radians per second, the actual speed of a particle is v equals omega r. So the further out I am from the middle, the faster I go. So of course everything's on the surface, but up here the effective radius is smaller than the charges here. But anyways, the point is that moving charges are a current and they create a B field. So the spinning molten core is rotating charge, a current, and you get a resultant B field. And also, you may not know, number one, already the axis of the north south is not exactly uh, parallel to the Earth's rotation axis. This is called the declination angle. And it changes. You need this if you use a map, a really precise topographical map, and you're using a compass and you want to know which direction true north is. You take your compass reading, and then you have to add or subtract the declination depending on where you are. And the reason, and also, um, it doesn't always point in the same place. And that's because, number one, the Earth itself, it's called precessing. So you may know about a North Star. Well, 10,000 years ago, the rotation axis of the Earth pointed at a different star. So that means that if you think about the yolk side of a spinning egg, if I start changing my axis of rotation of the outer egg, if you remember gyroscopes, the inner rotation is going to resist that change, and so it's going to do what it wants to do. So you have this constant symphony of these two rotational axes are changing, and they're coupled. I don't know if you guys, it's coupled by a thing called angular momentum that you were supposed to learn about in 2100. I don't. It's usually we don't get that far, and torque and tops and things. But anyway, that's why the Earth has a magnetic field. It's all very the real world is fascinating as hell, man. I never understand why people want to believe in conspiracy theories. So it turns out people like Michael Faraday, because we thought in the beginning of electricity and magnetism as two different things, Michael Faraday is the person who's given the principal credit for this concept that if you have a current running in a wire, then lo and behold, we notice that there's a magnetic field around that wire. So let's take a look here. We'll see what camera does the best. I got, and this one, oops. I have these really, I don't have blackout shades, but my experience of this room is it's pretty dark other than the artificial lights. This is a really old camera here. It's like 1990s vintage camera. You can see here out of the digital SLR that it doesn't make the windows aren't quite as bright. But you have to deal with it. You have to play the cards you're dealt. So let me get this a little bit bigger. And so it's just a sort of toss up of which camera is going to give us the best view at a given time. So, but what I can do is I can take, what's neat about using my cell phone is I can actually see what you guys see on the screen of my cell phone. So I've got this wire set up here, and I've got a compass. And of course, normally the compass points to magnetic north. Excuse me. And then if I have a real magnet, I have a magnet here. So you can see I have the South Pole, and just as we were told a little while ago, that attracts the north end of the compass needle. So I can put it by this wire here. And in fact, I wonder why do I have, it's always a question of making sure I don't have any other magnets nearby because the compass is quite sensitive. It has to be because the Earth's magnetic field is very weak. So I'm just looking around if I have, here we go. Got these little button magnets here. I didn't realize. Yes. And so the compass knows about them. And so let's get those out of the way. And no, it still doesn't want to point to what I think is, and I got my magnetic coils turned off. So let's see one more time just to, okay. So now it's decided, do I have a, no, it doesn't care about me. Okay. But as I come in here, it deflects a little bit, and I don't know why. Oh well, but we're just going to apply a magnetic field that's just so much stronger that it won't matter. Okay, so let's see. So it looks like the way I have this set up, that, and I have a power supply there, this is going to send current through this black wire from left to right. So let's take a look. Oh, look at that. So now the compass is with the current going from left to right. We notice that the compass needle is pointed away from us. And if I go around to the top, notice that it's now pointing towards us. So that is telling me that on the top of the wire, the magnetic field is pointed that way towards us. And on the bottom, it's pointed away from us. So then I go back up to the top, and there it goes. So now I can take my switch here, which I've wired up with this crisscross. It might be a little, so at the moment, the red comes in from the power supply. And then, oops, come on, you. Then it goes to this pole here. The wires are getting warm. I got to be careful. And then I rocked it forward so it goes to this pole, and then it goes out here to the wires by the compass. And then I've wired up this crisscross. So then now, when I flip it the other way, the positive is going to go to here, and that is, oh, excuse me, the the red will be now connected to this black over here. So it'll switch it. So you have black on the left, red on the right, and there I have red on the left, black on the right. So that reverses the current in the wire. So again, we're going from left to right, and as the red arrow shows, and now I'm going to switch it from right to left. And you kind of see since it was already pointed somewhat in the direction that towards us, it's not as dramatic as it was before. But of course, then I can go up here, and then we see how it reverses. So now in this particular case, with the current going from right to left, that tells me that at the top, it's going away from us. Come on, you. And then at the bottom, it's coming towards us. Here we go. Now, this engenders a right-hand rule. And, oh yeah, I'm using my left hand. No wonder it doesn't work. I'm going, what the hell, man? Ha! So, and that's right-hand rule. So maybe this camera might be too jumpy for this now. Right, so I can I can switch to the other camera for a minute. But maybe this one will work if I set it up right. Let's see. Oh, come on. Oh, yeah, that one. Oh, in fact, I can zoom it a little bit. Right, good. So, if I point my thumb in the direction of the current, my fingers will go in the direction of the magnetic field. So the current is the red arrow here. Yep, away from the camera, the lower right camera. And the, let's see, this camera here will get us an overhead view like higher up. Let's see. Ah, beauty. Okay, so in that case, this thing is facing the wrong way, this sun. So when the current is going, whatever direction the current's going, you put your thumb in the same direction, and that gets you the B field. So in this case, for the camera on the left side, that's like this. And this is for the camera on the right side. Oh no, wait a minute. Oh wow, wow, it works. Ha! Isn't that cool? I didn't even realize that. They're mirror images of each other. So when I go on either side, I see, oh gosh, coolio. It is correct. I'm better than I thought. Huh? Then I switch the current the other way. And now it points like this. So I got to turn my doodad around. And I point my thumb in the direction of the current, which is left to right. And when, say, in this camera up here, and you see the B field is like so. So that's basically a right-hand rule that I don't believe it's just an observation. And I was just thinking of this morning. I was I may have mentioned to you, or I will when we do the E over M, I guess next week, that there's the cross product and right definition of a right-handed coordinates was arbitrary, but we I think maybe that this is a fundamental observation, right? There's not Mother Nature doesn't give a shit. If we define a magnet a certain way, okay, that's a strict definition. We've defined the current a certain way, and so we notice that if the current goes in a certain way, then we're going to see this B field. And now the next step is forces on wires, and then you have forces on charges and then forces on wires. And then we use a cross product defined in a right-handed. Wow. Sorry, I just I can't turn my brain off. But this is the kind of thing, though. If you want to go play, if you want, even as an engineer, uh, if you're really interested in being like going on to like a master's degree level or something like that, you have to you have to be curious and think about these things. It's easier to be like that in a job as a scientist. Engineers are expected to produce things at deadlines and such, but it's still a useful thing to be inquiring and curious. Right. So you see here in these two illustrations, if the current going up, if you can hold your right hand over here, you'll see the compass is on top, right? And so if I hold my right hand with my thumb along the current at the top of the wire, the magnetic field points to the right. And if I reverse it, then the magnetic field points the other way. Okay, so I don't know. I made a copy of this, but I don't think I need that one anymore, but we'll keep it around. So, yeah, we have this Biot-Savart law, but I don't think you could, that's just a mathematical formulation. And I'm not going to get into it too deeply today. I just borrowed these from a lecture, yeah, from last spring. But you can sort of develop the concept, and and you end up with the field around a wire here, and then a nice little tree, a nice little picture. And notice it gets weaker. But it goes as 1 over r, not 1 over r squared. So what do we got here? So this is just another manifestation of it. Oh, right. So this is lining up the compass with the Earth's magnetic field. And then at some point, now this is one of the principles of the lab. If I have an unknown field, and then I apply a known field, and I get the compass needle pointed at 45 degrees. So we have B known and B unknown. What do we know if the angle between the compass needle and the known field, and hence the unknown, is 45 degrees? What do we know about the known and the unknown fields? Anybody? This is always interesting because we can be super good at math, but when we apply it to physics, we get a little confused. So type it into the chat window if you have an idea. When I set up these conditions, what do I know about the known and the unknown field? I want to see who has an idea. Repeat the question. Okay. Wake up, damn it. So I have an unknown field, and in our case, it's going to be the Earth's field. And I set up my wire very carefully so that the unknown field is parallel to the wire. And now I turn on my current, which has a well-known equation for the B field. So B equals mu sub 0 times I over R, and what else? 2 pi? Yeah. So I know exactly the distance away from the wire I am. So I turn on a known field, which is so B known is perpendicular to B unknown. And I turn on and I adjust the current until the angle between the needle and the either or the known or the unknown is 45 degrees. So then what do we know now a relationship between be known and unknown. In fact, we know it always in a way if we know the angle, but we don't know the strength of the resultant. Huh? See, this is funny. You guys don't know, huh? All right. Well, think about it. It's a really it's you're gonna kick yourselves once you realize what it is. Anybody know what an isosceles triangle is?
A triangle that has all equal sides. Right?
Has opposite equal sides. Was that?
No, the exact same sides, all of them.
I think that's correct.
Oh, okay.
No, that's an equilateral,
Oops.
right? So when you have an equilateral, then by definition, all the angles have to be 60 degrees. You guys, I hope you know that if the sum of the angles of a triangle, sum of angles of a triangle equals 180, right? So an isosceles has two equal sides, right? So when I have a right triangle, if I say that this is 90 degrees, what does that say about what is the angle then in isosceles right triangle? The other two angles. I mean, I'm poking you in the eye with it, guys. Just say the obvious answer. That's right in front of you. Yeah, right, James. There you go. So that means then once we set these conditions up, the known field equals the unknown field at at 45 degrees, when assuming, of course, we were careful to line up the unknown field with the wire to begin with. Okay. Yep, that's I guess I put it all. Yep, there you go. So, right, one of the things you're going to do is double check this in the exercise, at least the ultimate. So then how is it, what happens when we turn it into a loop? So let's go back to the cameras. Oh, got to get this one turned back on again. It went into sleep mode. I'll get that on in a moment. I just want to configure this before I stand up. Okay. So I've got my black coils here again. And I have another power supply. Oops, that was weird. What happened there? I have another power supply that you can now see down below. And I have this thing set up so I can put some maximum horsepower into these things. Uh, but anyways, let's take a look now. So I have this thing set up so that when I close the steampunk switch here, the current is going to go around in a clockwise direction. Is if it isn't a look, can we use rotational motion from? Um, yeah, not. That's a good question. I have to think about that. I mean, not in terms of physics 2200, that's for sure. So that might end your interest right there. But one can imagine perhaps that there's some angular momentum of those electrons. That's interesting. In fact, however, though, James, you give me a nice segue because a permanent magnet actually has you have a spin of the individual electrons, and then you have the orbital spin. So you think about, even though it's not exactly true, the electrons are orbiting the nucleus. And while they're orbiting the nucleus, they also are spinning like tops, and they have norths and south. And for the most part, since the electrons come in pairs, there's no net magnetic field. But in iron, there's a net electron north and south. And then the actual orbits themselves are also lined up. It's just one of those things with iron. And you wonder about, well, if we need a current to make a wire, I mean to make a magnetic field, how does the permanent magnet work? And in fact, it turns out that even in a permanent magnet, you're talking about a current, and it has to do with the spins of the electrons. So think about that blob of matter in the center of the Earth spinning, and then also simply the electrons traveling around the nucleus, just like these coils of wire. So James, it's his question is probably um, not from mechanics, but from what we're about to talk, what we're going to see in a moment. A current in a loop creates a magnetic field, and in fact, there are currents in um, all materials in a way. But usually they all cancel each other out, except for iron. In fact, this is it seems to violate conservation of energy that a thing can be a permanent magnet, because if there is a current going on in there, why doesn't the current die out? In fact, it also goes to why is it that you take a proton and an electron, and if I let them go, you would expect that they would charge at each other and just crash into each other. But when they charge at each other, they actually form hydrogen. And why is that true? And I'll talk about that in a minute. It's just incredible. The reason it happens is just would blow your mind. It just it's so intriguing that Mother Nature would obey this rule. But it made me think yesterday about what you may have heard about zero point energy. And this is an example of zero point energy, but since there's no way to extract the energy, when people are asking you for $100,000 to invest in their company for free energy, you run, because there's no known way to extract this stuff. Okay. So I'm just getting rid of this wire. I guess I picked up the telephone too soon. And so now, if again, I can start the current going around, in counterclockwise, clockwise. And so if I take my right hand and put my thumb in the direction of the current, I would see that on the outside here, the magnetic field lines would point at me. But then you also notice that they're going to point away from us in the center. Of course, they'll point towards the, if I get my hand in just the right orientation, of course, it'll point towards the middle. But if you think about it, the ones pointing towards the middle will cancel each other out. The ones pointed away from the middle, like that, will also cancel each other out. And then you're left with the ones pointed towards us on the outside, which will add together, but they're spread further apart. On the inside, they all point in the same direction as well along the axis of the coil, and they don't have anybody canceling them. And in fact, what I do is I put two of them, and that's called the Helmholtz coils, and we'll learn about that next week. But you end up that they all add together going in and out, but most especially in the center. And I said in and out, and in this case, away from us. So that leads us to our other right hand rule. And in this case, what we do is we put our fingers in the direction of the current now in the loop, and our thumb points in the direction of north. And we can take a look at this. So remember, in this case, since I've said that it's going around clockwise, then I expect the north to point away from me. And let's keep my fingers crossed that I wired this stupid thing up right. And there it goes, kaboom. And now another thing to watch, which is cool, is that as I move outside and I go around to the side, just as we predicted, it's pointed the other way. And that's, remember, because the north and the south, it goes out there and it has to come round. And they have to, in this case, there's no bar magnet, but they have to stay together. And one line has to be continuous all the way through. And what else? Oh yeah, so I said I would tell you about magnetic force. Now I have, let's see, this is always, I always think about this in terms of the Roadrunner and Wile E. Coyote. So of course there is the end of that hard drive, but it was garbage anyway. This magnet is so powerful. I'm gonna set the camera down for a minute. There's this one episode of Roadrunner where the coyote dumps this bucket of this big box of self-guided rockets out of a balloon, and then throughout the whole episode, something bad will happen to the coyote, and then at the end of it all, uh, one of those rockets shows up and blows up. And this magnet, this huge, this thing is ridiculously powerful. This magnet. I mean, I let a student play with them, and he cracked a couple of them because it's so powerful. But it's always interesting. You turn on the magnetic field in here, and I let students hold on to this, and they're always weirded out by the twisting force. And we're gonna this yeah, it's really amazing. I mean, I can let go of this, and you see that it wants to go back. Uh, we'll discuss another time that at this point it's interesting. The torque is maximum at 90 degrees and it goes down to zero at 180 degrees. So you can get it to stay there. And since this rough wood um, is got a pretty this magnet can stay there, but if I put it on a slick surface, I just need a little bit of manipulation. Now, the thing is, though, this magnet, notice it's not going anywhere. And the reason is that the magnetic field in the middle here is very, very constant and even. So there's no magnetic force. And I'm surprised that I don't feel anything here. Oh, a little bit. Okay. And so it has to do with when the magnetic field lines are not evenly parallel. That's when a force arises. But anyways, that is for another time. So let me make sure. Let me think through. Oh, right. So then at as I was saying earlier, the normal lab, and I got to get this thing out of the way. Hopefully, if I don't remember that thing, then it'll like slap onto my belt buckle, or it just causes havoc. Here it is. And like I was saying, I want to test this out. I may have to do it via YouTube video, but you can also see that guy is just sort of randomly rotating. The orange is there's some garbage color. Picked up some pieces of metal. And so when I hit it, now you see it has a it sort of oscillates, and you can actually time the period of that to figure out what's the strength of the magnetic field. Now I turned off the power, and now I reversed it, so now the north is coming towards us. We'll talk about that more next week with the over M lab. Are magnetic fields on top of electric field lines? Magnetic field lines are at right angles to magnetic field lines. Electric and magnetic, yeah. But remember, there's no electric field lines. No, maybe not remember. This is something that gives people trouble. And it's also one of the dangers of thinking about when you think about power, batteries, and power supplies, thinking about them as pumps. It's okay in a way, but they're circulators, uh, and they don't. So, and even though a battery sort of in its chemical reaction creates electrons, in fact, really a battery separates um, protons and electrons and creates a potential difference. And so, but you should always think of it as adding potential energy. But the point is that when you connect a wire to a battery or power supply, there's no change in the net charge. So there are no electric field lines around uh, um, a wire. You have to have a net charge. Now, having said that, though, wait a minute. Be careful, Harry. There has to be, though, because that's why sparks happen. Well, yeah, but the electric field lines will, I'm pretty sure, yeah, they'll be at right angles to the B field line. Ooh, okay, so now I've got another thing to think about. But to be sure, there's no net charge. So a wire doesn't have an electric field because there's a bunch of electric charges in it, because there's no net charge. What can happen is that if I have like if I put a metal shell around the wire, then I have a potential difference between the wire and the shell. Then I have an E field. Now you can even a wire alone, the outside world is zero at infinity. So there is a weak electric field around the wire. But we generally, unless we get up to many thousands of volts, we don't generally think about it. What happens is if you have AC, like the big power lines, it's the magnetic field. Ironically, even though we said about the forces, the magnetic field around the wire is always stronger than the electric field. Wow, James is on a roll, guys. If we were in person, I'd put a little gold star on his forehead. All right, let me think. So, I'm spending a lot more time well, I actually would have brought this apparatus with me to lab in the real world. Um, so you guys, you may have noticed that I have up on the platform there a tangent galvanometer. And you guys have the virtual one. And so I have it in my mind that I will set up the real one so we can have a look at the results. And let's take a look at the manual, the CAT manual together. And let's double check. Oh yeah, so at the end of the day, here's the enunciation of that right-hand rule. You put your fingers in the direction of the current of a loop, and your thumb points north. And you see that mu symbol. We'll talk more about the mu symbol next week. That has to do with forces on coils. We'll talk a little bit about it. I have to think about, magnetic moment. That's right. Okay. The original manual just does a hack job on that. But for now, let's just focus on this tangent galvanometer. And let's get this back up. Okay, part one, addition of fields. Right, so I've talked to you guys about the principle of linear superposition. And so meaning that if I'm at a given point in space, the field strength is just the linear sum of the different fields from the sources of the different fields. They don't have any effect on each other. So in the example of two spotlights passing through each other, it's bright where they cross, but once they pass each other and I look on the floor, the spotlight brightness of one spotlight on the floor has no effect on another spotlight. It only has an effect where they cross. Let's see. Two, the field at the center of the loop is determined by the number of turns. Yep. So there's formula. That's right. I had put that up here. Let me just go back to it. And I just sort of glossed by it. That's no, maybe I didn't. Where'd it go? La la la. No, I didn't gloss by it because I don't even have it. All right. What happened to it? Here it is. There we go. This is this kind of complicated derivation, but if you specify only at the z-axis, it gets a little simpler. Okay. Shown is we wish to calculate the magnetic field. Right. So here it is. B sub z. And this must be, at the very center, it's z equals 0, right? So then if you know the number of turns, you know the area. In this case, A is the radius, not the area. Then you know what the strength of the field is. And of course, you have the mu sub 0, the fudge factor. But it's still pretty cool. You have a certain current. You have so many turns in wire, and you can calculate what the field is supposed to be. And it works. Okay. Let's see. Let's get back here. And according to and then we'll determine experimental horizontal component at the virtual location, sure. And that's in Bermuda. I wonder why. And right, so now addition of the fields. And yeah, this is nice. So again, you go through this thing, you write down what you've done in each step. And if it says a question, instead of writing a question and answer, you say, we wanted to know what would happen if this happened or that happened. And let's see, confirm the field at the center. Nice, nice. Okay, this is sweet. I like this. So you can adjust the number of turns. Yep. And we can look at Microsoft Excel. We can type these numbers in. And let's see, what do you expect? The number of turns, and we plot the tan of theta, and then which should the slope be? Where's the equation? Where is the equation? Here it is. The tan is the b of the earth is what? The slope? Where since tan should be to n and I. So we confirm that b by plotting and then plotting theta versus I, and but it doesn't tell us what the slope is supposed to equal to. I'll have to double check that. No, it's weird that they don't give you the explicit. Well, they tell them this is for high school kids, so they have this Scraffer equation. But I want you guys to do make your own graphs. And yeah, I'm going to shut up in a little while. Oh yeah, so you need to look up the latitude and longitude at where is it? Hamilton, Bermuda. And it also turns you on to a website to convert to get decimal because the degrees come. Where is it? It's pretty, and it's not hard to convert these things. So let's do an example here. I'll do an example for you. Let's see what we got here. Right, so we're gonna blow this off. Last semester or this, I didn't know about the CAT simulations until I'd already asked the students to spend some money. So I sort of did the lab myself, and everybody watched me. But now we can learn a lot about these fields. So, for example, now we're supposed to get the inclination. This is at my house. So it says 58 degrees, 55 minutes, and 8 seconds. And so how do you convert that to decimals? It's really not hard. So that means that it's 55 over 60. And oh, you know what? Maybe it's not. Maybe so that's one fraction, and then 8 is it? Oh, it must then be over 3,600, huh? Yeah. Well, I'm going to double check myself, but I'm going to turn you guys loose because I thought I was all here I was all confident, and now I'm not so sure. So what happens is this is an exercise in using the tangent galvanometer to do that 45-degree angle thing. And then there's you need the dip angle. If you think about it for a minute, that's why I had this. That's why I kept this picture around. Where'd it go? Oh, here we go. So you notice that we generally think of the magnetic fields lines as coming out of the very end, but they actually come out of the middle too. So you can imagine a field line sort of like this, right? So there's going to be a horizontal and a vertical component. And basically, we don't care about the vertical component. We just care about the horizontal component. But if we want to know the total field strength at the surface of the Earth, then we need to know both components. And so I have this thing called a dip meter. And you would have, What did I do with it? Ah, here it is. I need to keep that away from the powerful fields too. This thing will tell us the angle of the Earth's magnetic vertical component, and hopefully oh, there we go. It's got to be lined up with the Earth's magnetic field. And anyway, so it'll tell us, isn't it? It's kind of cool. It'll tell us oh, can you see it? Uh, there we go. It'll tell us the angle of the vertical component if you set it up properly. But we're at home now, so the idea is that they picked a place, and your galvanometer, your simulated galvanometer has an Earth's magnetic field, and so you have to set this thing up. Let's see. Right. Oh, you see the needle move, the compass needle? So you can set up the galvanometer in the proper way, and then you can apply power, and you can see the needle changes. Oh, and they give you this little extra view here. So you can get this thing so you hit 45 degrees. And then let's see, you need to, oh, will it go negative? Yeah. So you need to do both directions. So there's a reason why you want to do both directions. And you guys should think about that. Why do I need to bother going both ways? But Philip and I are going to see if you figure that out. And then you get the vertical component from this website, and the sea turtles. No, up here. Come on, here it is, right here. It's pretty cool. I didn't know this existed. Okay, so do you guys have any desire to break up into breakout rooms, or you just want to work, each of you work on your own and ask us questions? We're only got about a half an hour left, so of course you'll finish this up on your own. So we expect to see the background about the direction of fields, and then you've described your apparatus, you've got your step by step, you've been writing down. Don't have to write a novel, and then yeah, it tells you all kinds of. It's pretty much self-contained, and when I go mute here, I'm going to double check these graphs just to make sure there's no ambiguity of what you're graphing and what you're fitting for. Okay, so I don't have the chat window. Where'd it go? Ah, there it is. I'm down for breakout rooms. James likes the idea, because then you can talk with each other more. I think that's not a bad idea. Okay, so I'm just going to randomly assign breakout rooms. I'm going to ask Philip to bounce around with them while I take a look at some various little ideas here. Let's see, only two people. Why don't I? You're allowed to switch rooms. Why does it not have? Let's put. I'm just picking you by random noises. So now there's 333 and 4. Oh, there was. Oh, I see. I just didn't. I thought there was only two people in that room. All right. Anyways, I'm gonna shut up. That's right, Alex. That's basically only thing, and we'll just go do that. Answer the question. Remember to write it up as if you're doing the experiment, not filling out a worksheet. That's the only difference. And we're going to use Excel instead of their Grapher app. And when I open up the breakout rooms, you guys get working. I'm going to double check the graphs that they want and make sure that I thought I understood them, but I'm a little doubts creeping in. So I'm going to make sure so that we can all know that before we say goodbye to each other. It's getting time to go, isn't it? So I was looking over. Let's see, 1, 2, 3. I went and found a calculator, and I want to just 919. So let's see what they say. 58, 55, 8. Uh, oh, oh, look at that. Did I get? I wasn't far off. 91922, I said. Oh, I was right. So I just punched in some in the calculator wrong, huh? So I still got it, huh? I'm not, I haven't, it's been so long. Minutes and seconds, it's an old usage. How are we doing? How many? Oh, only a few people are left. Ah, okay. So anyways, these things are not exactly fits, but I forgot this is high school level. Oh, I see. There's two different indications of how many people are still here. So there's people who are still in the chat rooms don't show up in this tally box that I have. In the breakout rooms, I mean. So anyways, they ask you to make these plots, and I thought you were going to type in the actual current here, but you don't. They're asking you just to verify that tan of theta is linearly proportional to n and I, and it's directly proportional. And so I leave it to you. I've set it all up here for you, and I'm just using this is really not I. This is a slope, and I'm not even doing residuals or anything like that because you're just asked if it's directly proportional. So, in fact, this graph already pretty much shows that it is, but I'm going to leave it to you guys to figure out how it's doing it. And then it wants you to do a similar thing with current and make another plot. So you guys will make these plots in Excel, and if you can, and I'll write it up. Excuse me. If you can, we'll see if we can try using the OneNote notebook. But if not, you'll just put you can right. You can copy paste these graphs and tables into a document, into a Word document, and then you can upload that with your notebooks. I wonder if the other people notice what time it is. So you guys may need to go, but other than that, it looks pretty straightforward. If you have any questions, just let me know. And yeah, I would have had more going on, and I had to help Armand. Well, I won't say who, but I guess I give away too much already. I had to help somebody with getting their simulation to run. Oh, okay. You too. Yeah, Philip has to go. Okay, right, guys. So right, it's 1:25. So if you don't have any questions, you can take off if you need to. And we'll see what the people in the breakout rooms do. All right. But if I'll hang out if you like. I won't. I'm not going to end the meeting while those people are still in their room working in the breakout rooms. And if you wanted to, Armando, you can join. You have the ability to join another. You can join another room. You don't have to join the one you're. Oh, somebody just left directly from the breakout room. Okay. Oh, there's Anna. Right. So Anna, I was just telling people I was exploring these graphs, and they're not exactly fits. they just want you to demonstrate that this the direct proportionality. So you, I'm not going to tell you everything. I made the graph, and where is draw menu? Right. So I set up a simple fit here where I just said that uh, I made a slope, and I multiplied it by the x-axis, which is the number of turns. And I would say again, this plot already shows a direct proportionality. It could be better, but I'll leave it to you to explain why. You guys are supposed to have enough sophistication to tell. But if I tell you right now that it's there, that'll help you to realize that if you don't see it right away, you'll see it eventually. If you don't have any other questions, please feel free to take off. Oh, there's Anthony. All right. Oh, Anthony had to take off. Oh, oh. So we just have Jacqueline and Romel, who may not even actually be here anymore. What time is it? Actually, I'll stop the recording.